All right, class, this is the end of chapter 11. This is what we'll be going over and probably be on the test for that matter. And most of you probably have a guitar or a violin at home, a string instrument. And this is what this is leading up to. It's called waves and strings and interference of waves and strings. So the first of all, this is not really a guitar. It's a coil spring. It will act as our guitar. And if I send a wave down like that, it tends to reflect. Now, the crest that goes, we're going to do this on the board in a couple of minutes, but the crest that goes down, wave crest like that, will reflect back as a trough. And a wave trough, if I can do it, that will reflect back as a crest. I don't think you can really necessarily see that. Maybe you can. We're going to do it on the board in a minute. But here's what happens. If I generate waves, what happens is they tend to go down, reflect, and then they interfere with one another. And a crest overlapping another crest will give you a bigger crest. A crest overlapping with a trough will give you an interference of zero, of balance out, equilibrium. And if it's a trough on top of a trough, it gives you a bigger trough. So this is what we call a first harmonic standing wave. Not very exciting. You have a point at each end which is not moving, and are partly moving, but not very much. And in the middle you have a maximum. That's called an antinode in the middle. Now if I double the frequency though, then this happens. If I can do it. Don't get old, class, don't get old. And there it is. I've doubled the frequency, and now I have three nodes. I have one either end, and I have one in the center. And between the nodes, you have maximum vibration, maximum crests and maximum troughs going up and down like that. If I can triple the frequency, if I can do it, I'm getting close, and I get the next possible standing wave. Now, when I first came here, I was 27 years old, young fellow, all that testosterone, all that virility, and I could do this stuff. But let me try it one more time. The first one was simple, the second one, total of three notes. Now we try it again. If I can do it, if I can do it, if I can do it. I'm doing it! Hey, look. Enough of that. And my assistant is over there kind of smiling. Because I'm not exactly 27 years old anymore. All right, my assistant, you come on back over here. And we're going to try to explain this on the blackboard, the whiteboard, rather. First of all, here's a wave. Looks like this again. There's the crest, and there's a trough. And what happens when this crest goes down and hits a fixed object? It will tend to bounce back as a trough. So it goes through what we call 180-degree phase change. If you have a trough and it goes down there, like that, and hits a fixed end, it will reflect back as a crest. So it goes down as a trough and comes back as a crest. Again, what we call 180-degree phase change. Actually, what happens if you have a crest overlapping a trough? The crest is trying to drive things up, the trough is trying to drive them down, and when they meet in the middle, you get, just at that moment, you get zero. Well, this point right here is called a nodal point, N-O-D-A-L. And the points in between where you have maximum activity, they're called antinodal points. So let me try again. It's in the textbook, by the way. And in your textbook, it's on page about 11-11. You all right? It's on page 11-11. And this is what happens if you run excessive waves down. This is called the first harmonic. Wave, and you have a fixed point at each end, and they call them nodal points. And that's an N for nodal. Like that, and then in the middle you have a maximum that's called an antinodal. Now if you double the frequency, what happens is you'll get something that looks like this. Goes up and down like that. You have 3 nodal points. Here you only had 2. The second harmonic you have 3. And the third harmonic, you're going to have 4 nodal points. So if you dealt with the 10th harmonic, you'd have 11 nodal points. Now I don't expect you to remember that though, but I think you should remember this has 2, this has 3, and the next one would have 4. Like that. And then it goes up, and then it goes down, like that. Goes down like that. And there's the nodal points. And here are the antinodal points. Now I know this can be confusing. My assistant is shaking her head, yes. But here's something you have to remember, okay? The distance between 2 nodal points, this is the entire wavelength right here. So the distance between 2 nodal points is exactly 1/2 the wavelength. Now remember what the wavelength is? That's the distance between 2 repeating points. So this is actually equal to 1/2 of the entire length of the wave. So that's 1/2 wavelength, this is 1/2 wavelength. And actually this distance right here is equal to the distance between adjacent antinodal points. So these are also 1/2 wavelength, as it turns out. Now there's some problems on this. I think I wrote them up here for you. You should try these problems from page 11-18, numbers 14 through 19. And what I'm going to do is do one of these problems for you. And then you have the homework problems that you have to do. And I'm going to ask my assistant, is that okay if I erase this board right here? This first board?
Do you want to go over that, or just want to erase it?
I'm going to just use this. I'm going to erase this now.
Okay.
Now that information right there, and my assistant has been trying to be very quiet, but she is the boss. And she knows that, and actually, class, you know that because I tell you that all the time. I am the talent, but she's the brains, and she's the boss. And she's telling me to move on now, okay? So we're on page 11-18, and I'm looking at one problem, looking at problem number 19. So let's give this problem a try. And again, I know this is confusing. And they're going to have tutors. I'm probably going to send you an email about they have some tutors to help you with this information. I know it's really difficult. It's much better if we were able to meeting face to face in class, because then I would show you something and I'd say, any questions? And somebody's bound to raise their hand and say, yes, I don't understand a thing you're talking about. And I'll say, well, I'm going to try this again. And hopefully it'll work better the second time. I'm on your side, and I'm always saying that to you. So this is page 11-18, and it's problem number 19. Page 11-18, and it's problem 19. So I'm gonna read the problem very, very carefully, which is what we always do in class. And it says a frequency of 120 hertz, 120 vibrations per second, that's the frequency, produces a third harmonic standing wave in a string 1 meter long. So it's the third harmonic standing wave. Well, let me see, let's go back. How many nodal points were in the first harmonic? Good, 2. Second harmonic, 3. And the third harmonic, 4. So we need to draw that diagram. That's the first thing we're going to do. So step 1, draw the diagram. Gram of the third harmonic. The third harmonic. So what we have is we have this, and this, and that, and that. Remember, first harmonic had 2, second harmonic had 3, and this is the third harmonic, so you have 4 all together. And now I'm going to draw in the wave. There's wave like that, and then this goes down, that goes up, and so you end up with something that looks like this. Just like what I was trying to show you with that coil spring a little while ago. And then what you do, you say, oh, what was the distance between adjacent nodes? A half a wavelength. And so that's a half a wavelength. Like that. And now there's another formula we have to remember from a while ago. And it was this. The frequency is equal to, the velocity is equal to the frequency times the wavelength. And tell me you remember that. All right? Now there's another form we need, and those of you who are familiar with guitars or violins are aware of this, because as you increase the tension in the string, the frequency will go up. And there's a formula here, it's in the book, it's on page, let me see if we can find it now. It's in here somewhere. Going back. So where did I put it? And this is on page 11-12, and it says the tension, the force or tension in the string is equal to V squared times the mass of the string divided by its length. So F sub t, I usually call it F sub t. F sub t is the tension in the string, is equal to velocity squared divided by the mass per unit length. And that can be derived, but I don't think you should worry about that unless you decide to take a higher level physics class, and then your teacher, I'm sure your teacher will go back and derive that particular equation for you. So now we have to go back and read the problem again, which is what we always do. We read the problem once, and twice, and 3 times, and then we try to solve the problem. So we read the problem, we found out it's third harmonic, so we know this. So we have that, and now we're going to try to use those equations to solve the problem. So I'm going to go over here again, and I'm going to read the problem again. And it says the string is 1 meter long. So the string is 1 meter long. So what's the distance between the nodal points? Well, this is 1/3 the length of the string, another third, and another third. So this distance right here is going to be equal to 1/3 the length of the string. And that's the distance between two nodal points. Well, that means that right here, 1/2 wavelength will be equal to 1/3 the length of the string. Now it says the length of the string is 1 meter. So 1/2 wavelength is going to be 1/3 times 1 meter. And now you get out your calculator and you find out, you multiply both sides by 2, and so that means the wavelength is going to end up being 2/3 of a meter, like that. And that's important. And my assistant is talking, but
That's the wavelength.
that's the wavelength. the wavelength would be equal to 2/3 of a meter. Like that. The wavelength is equal to 2/3 of a meter. Class, 52.5 years of marital bliss. and she's giving me bad looks right now, all right? But let's move on. We're having fun doing it. Well, I'm having fun doing this. I'm not sure if my assistant is having fun though. So let's read the problem again. And this is what, the third time? Sometimes we read the problem 3, 4 times. This is the fourth time? A frequency of 120 hertz, 120 vibrations per second, produces a third harmonic standing wave in a string 1 meter long. The mass of the string is 5 times 10 to the minus 4 kilograms. Well, we're going to change that to make it a little bit easier for you. Part A, draw an accurate diagram to determine the wavelength of the waves producing the standing wave. So we did that. There's the standing wave, third harmonic, 1 meter long, 1/3 the length. It's equal to that. Half wavelength would be equal to 1/3 of the length of the thing.
Mm-hmm.
And so that comes out to be 2/3 meters. So we have that.
Yay.
Okay. Now it says determine the velocity of the waves. Well, we need a formula. And here's our formula right here. So this is going to be part B.
What
Part
formula
B is
that?
determine the velocity of the waves. So part B is going to be the frequency times the wavelength. This is 120 hertz. Hertz is named after a physicist by the name of Heinrich Hertz. But 1887, he actually discovered that radio transmissions are waves, radio waves. And so that they decided to name it after Heinrich Hertz. And we know that the wavelength is 2/3 of a meter. So
Wait.
120,
Which formula is this?
this is the formula right here. Velocity is equal to the frequency times the wavelength. So it's the velocity is equal to the frequency times the wavelength. But they tell us what the frequency is. Frequency is 120 vibrations per second. The wavelength is 2/3 of a meter. And so that means the velocity is going to be equal to 80 meters per second. Now I'm not going to read the whole problem again, that would be probably the 5th time, but let me just read the last part now. The last part, part C, says figure out the tension or the force in the string. So we need another formula for that. Well, fortunately, we wrote this on the board earlier. And this now is part C. So this tension, I call it F sub T, T for tension. That's going to be equal to the velocity squared, 80 meters per second squared. And it says the mass of the string is 5 times 10 to the minus 4 kilograms. Well, most of you get confused when you see power of 10 notation. So I'm going to write it out this way. It's going to be 0.0005 1, 2, 3, 4 meters, kilograms rather, kilograms. That's the mass. And the length of the string was 1 meter. And so we worked that out using our calculators, and when we worked that out, we should get an answer of about 3.20 newtons. 3.20 newtons. Now the homework problems are on page 11-21, and actually a good problem on strings is page 11-21 is numbers 24 and 25, and those are the 2 of the homework problems. So for homework, they're going to be page 11-21, page 11-21, gonna be problems number 24 and 25. Now, we're almost finished with chapter 11, but I think we should make a mention of something, that there will be colleges setting things up for tutoring, okay? But the thing is, hopefully you're able to get a hold of these videos on Blackboard. And please let me know if you are. I know this is, I think, doesn't compare really meeting each other with each other in face in class, so you can ask questions and tell me to slow down or whatever, and make honest suggestions about how I'm doing and how you're doing. Here, I've always been here to help the students. And if you try hard, I really want you to do really good. I want all my students to do really good. So I'm gonna be getting hold of you. I'm gonna probably send you email, my regular email, and with more information about the problems that you should be trying. But hopefully you can go on Blackboard and you can view things on Blackboard. That's really important since we cannot meet in person. And that is enough for today, okay?